Hey everyone, in this video I want to talk about how we can think about architecting our solutions in Azure to meet the requirements in terms of service level agreements, availability of our application. Now, while my examples of components will be Azure, these principles pretty much apply to wherever. Now, in the past, I've done videos about, hey, availability zones, availability sets, using multiple regions, load balancing, both regional and globally, understanding composite SLAs. But all of those different capabilities, how do they really come together to solve meeting the requirements of my application? So that's the whole goal of this video. Now, when I think about what are the requirements of the application, I have to be able to verbalize, I have to be able to document exactly what are the components of my application and exactly what are my requirements. So I have to make sure I know my services architecture. What are its dependencies? How do they connect? How do they communicate? Is it a tight coupling like an RPC? Or is there some loose coupling, maybe via some queue or service bus? If I can't draw a picture of the component, so I want to be able to say, hey, so I have some client component, and I want to understand what those clients are. Hey, well, that client connects using HTTPS to some endpoint. Well, it initially goes to some kind of load balancing solution. Behind that load balancer, hey, I know I have some web front end tier, which is actually application one, we'll call it. And then it goes and talks to some back end database. But actually there's a firewall between the application tier and that database that those connections have to go through to actually go and get there. So I want to know all of the different components that fit within that solution. I'd want to know things like, hey, well, actually from a dependency perspective, today it uses some identity. So there's a certain set of interactions between my web front end and my database. Maybe there's something else going on. Maybe I deploy using a certain tool. Whatever that is, I need to understand all of the components, all of the communications, everything in between them. I want to understand what are the ratios that I would expect. For example, hey, there's going to be 20 app servers for every one database server, for example. There might be other middleware tiers in that as well. So there's going to be different ratios. And why that's important is often in development, we just do a one-to-one. Hey, we have an app box, and we have a database. If in production, it's 20-to-1 or 100-to-1. Maybe there's some mesh going on between a certain tier. Well, that's a huge number of connections that having one instance is not going to test. So I really want to make sure I understand all of these elements, which is why that whole KISS, can keep it simple, stupid. The simpler we can make it, the less concepts we have in all our architecture, the easier it is to understand and likely the best chance we have of actually keeping it up and running. The more complex we have it, the more likely is just through sheer, hey, we never saw that, we didn't know, things are going to get missed, which will then become a problem. There are tools. There are things that maybe look at the network communications to work out dependencies. There are things that can look at API calls from within the code to work out dependencies. Nothing's foolproof, but there are things to help. And then I need to think about, well, for my application, so my all-up service, that complete service, what are my requirements? And my requirement might be, hey, we always talk about a number of nines. You'll hear 3 nines and 4 nines and 5 nines, and that's really the percentage of the time it has to be available, i.e. something can communicate to it and get a response. It's available for that percentage of the time. So I might say, hey, I need 99.95 is my SLA. And that's maybe in non-maintenance windows, because maybe my application does have a maintenance window. Maybe, hey, from Sunday to 1 to 2 a.m., there's a maintenance window available to me. What are my seasonalities of my application? Hey, it's super busy from maybe 5 p.m. to 10 p.m. Maybe I'm some kind of online pizza restaurant. there's a bigger seasonality when it's Super Bowl. I want to understand all of the different elements of my application. I need to really understand all of those things. What's maybe going to impact the capacity, the load that's going to happen on my application. And Microsoft has a site, I mean, these are standard concepts. If I go and look at SLAs, if I'm just curious, so here we can kind of see, hey, well, we're 2 nines, so it's available 99% of the time. So it gives me a certain amount of downtime per week, per month, and per year. And obviously, the higher the SLA was going to be available more, so the less amount of downtime we expect on a weekly, monthly, or annual basis. And the whole point of these SLAs is most services will provide you with an SLA. In the case of Azure, for example, that SLA is based around a certain financial guarantee. If it breaks that SLA, then there's a certain amount of service credit you would get back. So the SLA gives you this financial backing and it gives you some idea of what they expect to be able to deliver in terms of that availability. Now, do I understand all the different types of failure that could occur? There are very obvious things. Things crash. That's probably the most simplest idea. And when I think about crashing, well, hardware crashes. The server, the disk. But also remember, that server lives in a rack with a top of rack switch and a power supply unit. Those can fail. They live in a data center that has air conditioning and power. It has networking. Those elements could fail. So the entire data center could fail. A rack could fail. A server could fail. An operating system could have an OS crash. My application could have a crash. Some dependency could have a crash. But they're very simple types of things. There are others. I could have a CPU or memory pressure. It's not crashing, but there's increased pressure on my system. Do I have a disk or a database being full? Is there some traffic surge? And maybe that's valid. Hey, it's just had Black Friday here in the US. Tons of people are coming to buy my latest bargain. Huge amounts of traffic coming to the components. There's this huge surge in traffic. Some network flood. And maybe sometimes it's because of a bug. Something's just retrying and then the other thing's retrying. It floods my own service. When we talk about the network, well, DNS fails. Some load balancing solution fails. And again, we talk about failures. We're talking about traffic surges. Maybe it doesn't fail, but maybe my latency when I'm doing certain operations just increases. And many times when the latency starts to go up too much, it really becomes indistinguishable in terms of the user, the end experience of, hey, it's failing. So we have these different types of failures that can occur, but it could also be completely logical, i.e. it's not anything actual failing, but maybe I'm trying to auto scale. Maybe my auto scale rule is wrong. I'm trying to scale up, but maybe I've run out of quota. So I didn't check these things before I started planning some event and just my subscription. Hey, it's run out of quota, so those things fail. Do my auto scale rules really work? If there is some latency, do I retry too quickly and it just sends me into some horrible death spiral of my all-up software? Do I really understand the different blast radiuses of different components? And we're going to talk about that. Do I have some independence between when I have multiple instances, maybe for scaling, we have them for resilience as well. But do they depend on some common thing? Well, they'll go through the same firewall. So maybe I've got 3 instances here, but if they all go through the same firewall and it fails, it doesn't matter anymore. They've got a single dependency, which is now a single point of failure. So whenever I think about multiple instances, I want to try and avoid any kind of common dependency around that. So there's lots of things that can fail. There always are. And when I think about trying to architect around these to give me resiliency, there are different factors that I really have to consider. So if I'm doing my architecture, what are the elements of my architecture that I really have to think about? Well, Obviously, there's the infrastructure. So I have, actually we do this in blue because it's Azure. So we have our infrastructure. And bear in mind, I'm saying it's in Azure. Maybe it's not. Or maybe some of it's in Azure. Maybe some of it's in another cloud. Maybe some of it's on premises. So we have the underlying services we build on. VM scale set, Azure Kubernetes services, app services, Azure SQL database, load balancer, whatever that might be. These are foundational levels. And realize as we talk about these, if I build my foundation on services that don't meet my overall application's SLA, I'm in a tough spot from the get-go. Now, doesn't mean we can't do it. We're going to talk about how different things come together. But realize that puts us in a weakened position right from the start. And then obviously we have our application as well. And realistically, it doesn't matter how much money and excellence I pour into my infrastructure. If my application architecture is, well, crappy, it's not going to do very well. I'm ultimately going to fail in whatever my goal is. Because if I've got poor decisions, if I haven't spent enough time developing it correctly, if I've not tested it correctly, if there's huge holes in the logic and the functionality of the app, it doesn't matter how stable I put it on, it's ultimately going to fall apart. And then realize for all of this, there's then just going to be, both for the infrastructure and my app, operations. There's things that have to happen to keep it running. Infrastructure's obvious ones. Hey, we have to patch operating systems. We have to update runtimes, update middleware. We have to, the underlying hosts themselves have to go through certain maintenance. Now, there's things we can do that, hey, there's rolling upgrades so we don't take down the complete service. It's reduced capacity, but even that we can solve with certain surging, adding nodes before we start taking those down to replace them. There's things we can do. .NET, J2E, Kubernetes, they need updates. Database, well, they need to have updates. They need to have upgrades. But hey, can I go and upgrade a secondary, then fail over to that, then go and upgrade the old one? Again, a rolling type upgrade. So there's never just a gap in my service. I'm switching things around. I'm moving things to counter to that. For my application, well, I don't just update my app. Typically, am I doing blue-green? I deploy to an environment, I test it, I warm it up, and then I switch. Maybe it's rings, so greater portions of my user population go to a newer version. Canary, hey, I have some testing, and again, it propagates out. There's different solutions to how we think about that. But I always want to make sure when I think about all of this, I always want to ensure that it's not one environment. I always need to make sure I have some partitioning all the way between what would be my non-production, and there might be more gradients, dev test, QA, user acceptance testing, production. But at minimum, I want to think about at least 2 environments, and I should never be rolling out the same change to both of them at the same time. Be it an OS, patch or update, runtime like .NET or J2E, be it a Kubernetes update, my app updates. It should always be going this way because maybe, hey, a new version of Kubernetes breaks something in how I'm interacting with it. Hey, the new version of .NET, it's breaking. I was using some undocumented API or it's been deprecated. I just didn't notice. I always want to be making sure I'm staggering the rollout so I have good operational practice. I have different environments to make sure if there is a problem, I'm going to find it. So never ever update non-prod and prod at the same time. Non-prod, test, and then ideally we have these rings, these propagation outwards. Now when I think about these 2 elements, in a lot of ways, the infrastructure is actually the easy part. So if I was to look at Azure, for example, every service has, as I mentioned, an SLA. So here, every service has a service level agreement. And the whole point of the service level agreement is, as we all like, it's financially backed. in terms of service credit. Hey, if they do not meet the service level agreement, hey, they're unavailable for greater than that amount of time they committed to, you get service credit based on the amount of time it was unavailable. Now, you may not care about that. The service you're running may be way more critical than I care about $20 back. But it gives you an idea of what Microsoft or any other vendor expects to be able to comfortably guarantee the availability of whatever that service is. Often it will be higher than that, but that's what they are committing to. Now realize this is the expected minimum availability. And what they're including in this are different types of event. Now, obviously, there are things that are just failures. The cloud is not some mystical on-air type of service that's resilient and never fails. There's data centers, there's racks, there's nodes, there's disks, there's switches, there's cable. Things fail. So based on the service, based on maybe the number of instances, based on how they're distributed, they get a certain comfort and certain resiliency that they don't expect certain failures to affect more than a certain amount, so they can offer a certain amount of SLA for those. But realize also built into this, for some services, there's just planned events. For example, if I just have a single virtual machine, well, they know there's going to be times they have to update the underlying host. Sometimes they'll try live migration. Often that's not possible, so they have to freeze the VM. It gets frozen in memory. It's going to be unavailable for, I don't know, maybe 30 seconds. It's getting smaller and smaller, but they know there's going to be some period that it just won't be available for. And we can see that. So if we go and look, so there's a whole document about SLAs. Great. If I was to look at compute, virtual machines, and it tells me here, hey, if I look at a single instance using a regular hard disk, so standard, the worst, so this is just a single VM, it's a 95% SLA. So it could be down, unavailable 5% of the time. If I use an SSD managed disk, which is a higher durability type of service, well, that now jumps up to 99.5%. So it'll only be unavailable 0.5% of the time they expect. And then like if I did the premium SSD or ultra disk, it now goes to 3 nines for a single instance. If I use availability sets, remember availability sets are different racks in the same data center, it goes up to 99.95. And if I use availability zones, well, now I get 4 nines. So it gets even better. So we can see those available and we can plan for that. So again, what is my requirement? So this is absolutely telling me what I can expect. So if I think about just some single VM, so if I just had a single VM connected to, let's say, the premium, well, I could get 99.9 SLA. Okay. But I know, well, if I created 2 of those in an availability set, which means they're distributed over different racks, fault domains, within the same cluster, the same data center, well, now I get a better SLA. Likewise, I know if I use availability zones, so hey, if I deploy 1 VM to AZ1 and 1 VM to AZ2, I'm going to get lazy and not draw the disk. Oh, I'll draw a disk. Well, now I get 4 nines. And why is this? Why is it they can do, when I use availability zones, a higher SLA? It's because what are the common things that could fail? Hey, when it's a single VM, it's a VM on a node. The node could fail, the rack could fail, the data center could fail, the whole region could fail. There's many different things that could fail. And the resiliency is really a factor of, well, hey, if it's using premium storage, they know the storage clusters are pretty good and resilient. It heals. Its resilience is it will heal. If the node fails, it will restart it on another node. If the rack fails, it will restart it on another rack. With availability sets, well, now a node or rack failure will not impact both of them. So I'm more confident I can offer that resiliency. If I use availability zones, they're in different data centers. They've got independent power, cooling, networking. There's very few things that could possibly impact them both. So I can do a higher SLA for those. And when we talk about these different levels of blast radius and our ability to be resistant to them, what this is really all boiling down to is in boats, you see, seen the movie Titanic, they had the bulkheads. So if I think about a boat, and I cannot draw a boat at all, but let's pretend that looks like a boat, and it doesn't like a boat. But they talk about this idea of bulkheads. And the whole point of a bulkhead is, hey, if there was some leak, if there was some break, and then water started gushing in, it doesn't fill up the whole boat. Now, when I have a single VM, I have no bulkheads. The quality of the disk makes the outer, the shell of the ship stronger. If it's a regular old basic hard disk drive, it's made of some sort of fairly solid cardboard. If I go to standard SSD, now it's made of wood. If I go to premium SSD or ultra, now it's metal with wood reinforcement. But it's still one big compartment. If it breaks, it's still going to flood. If I use availability sets, well, availability sets, it introduces these little bulkheads. So I've now got a certain level of resiliency that it can handle a node or rack failure. If I was to go and use availability zones, well, availability zones are bigger bulkheads. There's a bigger set of resiliency. So it could handle more types of failure and it still wouldn't impact the other compartments. It can't overflow. And I could even say, well, I can go beyond that. If I said multiple regions, I might say, well, the bulkhead's all the way to the top. So these different levels of bulkhead to protect me from different levels of blast radius, which is why the SLA can improve as we go through those. That's really the whole point. And you have to accept that those are the SLAs. I have a choice in the service I want to use. If I choose to just run a single VM with a premium disk, it's 99.9%. We know there's going to be certain things, both failures and planned events, that will result in some lack of availability of that resource. If there is a failure, if there is a node maintenance and my VM is unavailable for 60 seconds, if that takes down my application in an unacceptable way, you're not architecting to your application's requirements. There's no good being upset that, oh, my application's been really badly impacted in a way I can't handle if you put it on a single VM. You have not architected to meet your application's requirements. If my requirements of my app that I need to know are beyond what a single VM offers, I don't use a single VM. I use availability sets, I use availability zones. I have to architect to my requirements. And we can think about this, we can put it in a real world way. So let's take an example. Let's say I've got my house. So I'm living in my house. This is not my house, but let's say it is. And there's a road, and hey, the road splits off. And there's a train track. There's a train track that runs all the way down. And because of that train track, what we actually have is we have kind of a crossing right there. And it tells us, they publish this, they tell us well in advance, when they built the road, they had the train track, hey, 3 minutes of each hour, there's going to be a train coming through. And that's going to be closed. So what does that mean? Hey, they're telling us. So 3 minutes each hour is a 95% SLA. So I expect this road to be available and transversable 95% of the time. But 5%, they're telling us, hey, it's not going to be available for that period of time. Now, if I'm driving on this road and it happens to be closed, I'm going to sit at that thing and fume at the train, go, stupid train, stupid crossing. But I can't write a letter. I'm well aware that that's what they publish. Now, it could also be as part of my drive, as my drive continues, there's a traffic light. And the traffic light, hey, could be red. And my wife and I argue about if it's orange or green. I think I say it's orange. I think some people say it's yellow. But there's traffic light. Well, the traffic light has essentially a service level agreement that could impact me. Maybe 1 minute out of every 4, it's red because there's other cars. So that has a 75% SLA. And you realize that on my journey, I have to go through both of those. I need both of these to get to whatever my end target is. And so the relationship between these, well, it's and. I need both of these available to be able to go through uninterrupted and get to my target. So what is my overall SLA? Now, composite SLA is out of scope. I have a whole separate video on that. But essentially, the more things I have that have to be there in my path, they're ANDed, the worse my overall SLA gets, which makes sense. If I'm driving down the road, well, the railway crossing could be open. That would affect me. But I also maybe could get stopped at the light, maybe both of them. That'd be really unlucky. But there's a greater chance. The more things I need, the greater the chance one of them has a problem and will impact me. So the overall service level agreement of my journey is going to drop. So in this case, there's a 5% chance this could be down, and there's a 25% chance this could be down. So we have to multiply those chances of it being down. So because it's ANDed, my overall SLA of these things together decreases. It becomes a 71% SLA of that overall journey when I have those two things coming into play. Because they're unrelated, either one could impact my journey. So that's really the whole point when we think about this. And so if I take that same example right there to those SLAs, well, the same thing would apply to Azure services. So if I was to think, we'll go pretty basic initially. So if my Azure architecture had maybe a load balancer, because whenever we talk multiple instances, there's going to have to be some virtual entry point, a virtual endpoint that clients can talk to. Well then, hey, maybe I have a virtual machine scale set. Maybe that's an AKS node pool, whatever that might be. So load balancer checks which ones are healthy and distributes. And then maybe I've got some, hey, Azure SQL database. All of these components have a 4 nines SLA. So you might look at that and be like, oh great, my SLA is 99.99. I'm 4 nines, I'm done. No, you're not. Because remember, I need all of those things to be working for my overall service to work. So remember, we have to take the chance that it's down, so 0.0001 times 0.0001 times 0.001. So our overall SLA here for these 3 components that were all 4 nines, and my math might be a bit wrong here, but it drops. Now that's my SLA. Because any one of those components is a tiny chance. So it's 100% chance it has a problem. But now there's 3 chances that that could happen. So the actual overall SLA decreases because that is still pretty good, but it goes down. And then realize I'm saying simplistic because maybe there's an Azure Key Vault in here. Well, that has an SLA. Maybe I'm using managed identity with Azure ID. Well, Azure ID has an SLA. So all these things start to reduce my overall SLA. So the more parts we have, the worse my SLA will just ultimately get. So how do we counter this? Well, we talked about bulkheads. We talked about the idea of having these independent multiple sets of our solution. And so what I need to be able to do, if this was my car journey, what I'd want is, well, I want a second path I could potentially take. Let's just go, we'll go green. So there's another road. Now that road also goes through the railroad line. So it equally has a chance of the railroad, there could be an impact. It also has a 95% SLA. And to keep the math simple, I'm going to forget about the traffic light. Let's just say there's just this. We're only going this far. We're going to a building that sits before the traffic lights. So I'm trying to get to something right here. And the road curves off and comes to this building. And what they did very kindly is they've added a sign. And the sign tells me, hey, when is the next train going to go through each of the railroads? So it can advise me, hey, go this way. Go this direction, because Thomas the Tank Engine is about to be rolling around here. We know how long it's going to take you. Go down this path. And what has this done? Well, this has now given me an or relationship. I can go either way. So I can go through that direction, or I can go through that direction. If I know the train's coming or this has got a malfunction, I can go the other way. So although they both have a 5% chance of failing, the chances of them both failing is very, very low. Like that's typically not going to happen. So I would think about, well, yeah, to increase that resiliency, I would say, what's the chance of it being unavailable, and multiply those. In fact, what I said earlier was wrong. It's not, it's the 99.99 times 99.99 times 99.99. I just realized I said it the wrong way around. If it's the, I need them, if it's and, I multiply them together, which is going to make it decrease. Whereas, if it's an or relationship, well, it's 0.05 times 0.05. Because what's the chance they're both going to have the problem? So now the SLA of this or goes up massively. Now it's like 99.75 or something. So the overall SLA now is much greater than those independent parts. So the same applies to my deployment. I do exactly the same thing. If I had this idea of, well, there was my one deployment, hey, I'll do a second deployment. I'll have another isolated, and that's kind of the key point. I don't want any shared dependencies between them, because otherwise there's a shared dependency, there's a shared point of failure. But now I'll go and deploy, hey, look, a second load balancer, going to a second VM scale set, going to a second, now saying a second database gets complicated. I'm vastly simplifying this because obviously database has state. Can I just run some completely independent database? It really depends on what we're doing, but that's pretty tricky to do. But let's just say we can for this. So now we have this OR relationship. So it was 99.99 times 99.99 times 99.99. So it gave us this 99.97. But now if it's an OR, I can go either way. It becomes that 0.0003 times 0.003, which is basically 100%. I think it's like 99.99999 set 1. It's like 7 nines I'm getting to now, which is huge. It's like, wow. And obviously the more regions, let's say these were in different regions, the more regions I add, the better this gets. So this is just getting better and better as I go through. So each independent deployment has the same SLA. Both of these are 99.97. Again, 99.99 times 99.99 times 99.99. But when I start ORing between them, it's a 0.03% chance of it actually being down. And so if I can go either way, hey, I'm in a fantastic position. So I've solved my problem. Well, not quite. Let's go back to my road example for a second. How did I know which way I could go? Hey, this sign. Oh, so the sign is balancing. It's telling me where to go. Well, this sign, it probably has a certain availability. It has things that could fail. So maybe this sign itself, it has a 99% SLA. Well, now I'm back at that idea of, okay, so it's 0.99 times 0.9975. It's going to bring down my overall SLA again. Be like 98.75. And again, my composite SLA video goes through the detail of this. That's not the point of this video. But the point of it is, as I add components, if they're required, ultimately it will bring down my SLA. So while I had this nice OR relationship getting me to this great SLA, well, something has to balance between them. So if it's my sign, well, my sign has an SLA of 99, so straight away, I'm going to decrease my SLA. So I'm now reliant both of these, so this has to be here, and either of these. So that's these two SLAs, 0.99 times 0.9975, become my ultimate SLA. So it will always be slightly worse than my worst SLA of any individual component when I then have to AND the different elements together. And the same is going to apply to Azure. Hey, I drew in these completely two isolated instances. That's all very well. Chances are that doesn't just exist as some mythical, magical solution. I'm going to have maybe something like Azure Traffic Manager, which is DNS based. Maybe it's Azure Front Door. Well, both of those have a 4.9s SLA. And so while I have these multi-region deployments, I can use either one of them. I get this 7 nines, and I need a 4.9 solution. So straight away, it's going to basically bring me back to this. This is basically 100%, near enough. I'm going to come back to 4.9s because I have a reliance now on that balancing solution. So I'm straight back to here. Doesn't matter what else I think about doing, what else I can do. Ultimately, I'm here. It's like, well, that's a bummer then. Is there no other solution? Well, I'm not completely useless, no matter what my wife may tell you. So if I'm this person here, and realize there are other elements. I have a car, the car has an SLA. There's other things that come into play. But the sign's broken down. But I remember yesterday, and I leave at the same time every day, it told me to go this way. So even if this is unavailable for some reason, there are things I could do as the human. I have a cache. In my memory, oh, okay, I know. Yesterday I went that way. I remember the last result I got. Maybe I can reuse the last result. That may be an option available to me. Maybe there's, hey, some alternate path I could take entirely. Maybe I've got binoculars and I can see it's down in some way. Maybe there's a third road I could take. Maybe there's another way. Maybe I phone up a friend. Maybe I'm delivering something. Hey, can you do this to me? I jump in a helicopter. Maybe there's an alternate path that enables me to get to my destination. So exactly the same way my human has a cache maybe of what way I went, well, there's something here. There's some client. Now, when we talk about client and servers, realize that I'm drawing it as a client machine, like an end user impacting a service. But in a multi-tiered architecture, if there were more tiers involved, a tier could be a client to another tier and a server to another tier. So when we talk about caching, it's not just some end client to the service. The tiers of the service can do caching to other tiers and have alternate paths. I can do the same thing. So for example, here it's the client. Well, maybe it's Traffic Manager. And Traffic Manager returned me the public IP of a load balancer. Well, I could cache that. I could cache it and say, hey, actually that last time was some value. And if I don't get a response, if traffic manager's down, I'll just try the last IP I had. Maybe I could just go and query DNS and I get 4 records and I try them myself. So as the client, I inject certain functionality to counter if certain components are down. So now I can start raising my resiliency, my availability back up, because now it's an or. Hey, I'm using Traffic Manager, or I'm going to just fall back to my last result. If my car isn't working, I'll use my bike. Hey, if SQL isn't working, it's not available, maybe I go and write to a queue. And then it goes and does something later on. Or I've got a cache, or I've got maybe a write-through or read-through cache that caches the last sets of records, and we'll talk more about the caching. But there are things I can do in my app architecture to start countering, and that's really a key point. So when we think about all of the different elements involved of infrastructure, don't try and solve it purely through infrastructure. It's really a losing game. And again, it doesn't matter how great I make my infrastructure, if I do silly things in the applications logic, well, it doesn't matter. So hey, I've got the idea of a queue here. But realize to do this, my app has to be able to do this. There's extra work I'm doing in my application to have some kind of failover, but that's how I can start to improve my SLA. Hey, database is 99.99. Well, if I can go to a queue instead, if the database is down, well, now I'm ORing these relationships. So again, I'm going to improve my overall SLA, but hey, it means I have to have extra logic in my app to handle this. So I can really think about, at a pretty high level, there's just a scale. I have this great big scale of how I can think about the resiliency. And it really goes all the way from this, hey, I've got some single instance and maybe it's through to, hey, I do some kind of create, which I can do in the cloud, create, restore, maybe cold. Maybe I've got the idea of warm. Maybe it's hot. Maybe it's active-active. There's different levels I can do. So hey, I've just got a VM running. If there's a problem, I'm waiting for service healing to recreate it again and start it again. If it's cold, or maybe in the cloud, we can just create it. I need to go and restore something. It's not ready, I have to restore data. It's going to take longer to do this. If it's warm, hey, it's up and running, but maybe there's work I have to do to bring logs up to speed or move clients over to it. Hot, it's getting the logs, it's up to date. I have to just flip things over. Active-active, it's just running. But this scale, obviously, this is very cheap. This is going to cost more, so I'm saying expensive. This is going to be simple. Hey, it's something running in a VM. This gets more complex. When I try and do active-active, when I start to do those, hey, alternate paths, if SQL's down, write to a queue, hey, the client's going to cache things if something's down, read from the last thing, it gets more complicated. However, this is going to be a very slow recovery, comparatively. Whereas this is going to be fast. This is going to be a fast to instant, if I'm active-active, recovery. So we have these different levels. So I have to weigh up the cost of the resilience, the cost of the app effort, compared to the cost of the downtime. So it's a constant, there's not a right or wrong answer. If it's not a very important service, it's just some, hey, it's convenient when it's there. If it's not there, no big deal, I'll try again in an hour. Hey, I won't bother spending the hours to develop and have contingency and have multiple instances. Who cares? It's not that important. Sure. I'm meeting the needs of my app. Its SLA is 2 nines. Hey, if it's down, go and grab a drink. I'll restore it, create a new one, whatever. This is super, super critical. I'll lose millions of dollars an hour. Okay, I'm willing to spend the money to put in the dev effort to have these resilience things, to have this resilient infrastructure. So I have to think of all of those different elements. And I've said a few times now, the app, because as I mentioned, there are things I can absolutely do in the infrastructure. There are ways to make the underlying infrastructure resilient. I can improve the SLA. Yes, I can absolutely do all those things. But as we talked about, if my application is not very good, it doesn't really matter what I do in the infrastructure. There might be some things I can counter, but ultimately I'm on a losing battle. So what can I do in my app to make my app as resilient as possible? So the biggest thing, and we see this a lot now, if I have this single great big monolithic application where it's just one instance with one big process with very tight coupling and it calls a library, has to scale together. If something want to change something, everything else has to change that connects to it. That's really ugly. It makes it very hard for me to handle that. So if I can, we want to try and move to this idea of microservices, or at least split it up into some kind of more isolated tiers. So now I can have different tiers with different instances for the tiers. And having those different instances, one of the nice things that lets me do, obviously, is they can each scale independently. Because, hey, there might be that the web front end is super, super busy, very chatty. But then the actual processing of some request is far less frequent. I can have far less instances of those. So let's not waste a whole bunch of processes. So if I can, let's kind of split these up. I mean, if you look at the Azure well-architected framework, landing zones, those can all help with as I start thinking about these things. And ideally, what I want to be able to do is have independence. Remember those bulkheads? So we talked about the bulkheads for here. This was bulkheads for the infrastructure, the VMs, the scale sets, so split them over racks, split them over data centers, split them over regions. The bigger the bulkhead, the greater my resiliency that one thing bad happening wouldn't impact the other instances of the things. So in my application, it's exactly the same. I want to try and get cells. I want to get independent cells of my service. So that's cell one. Ideally, what I want is a completely independent set. And if something bad happens over here, it cannot impact this other cell. Often when we start to see things fail, so let's say I had a bad app and it was leaking resources. You often get these cascading failures because as soon as one instance fails because it's leaking resources and it's full up and crashes, well, what have I done? The load that it handled is now spilling over into the remaining ones that have the same bug, so they're going to fail even quicker. So you have this failure, and it will just accelerate. Well, I don't want that to spread to the whole thing. So we really want this idea, if I can have these isolated, I want to really think about there is a wall. There are no shared dependencies between them. There's really minimal chance that some problem can spill over. It's the bulkhead. It can't spill over and impact that. So it's going to help stop cascading failures. Something's happening, I don't want it to spill into my other cells as well. Now, this can get difficult. Certain applications may need a single point of truth for some things. If it's an inventory and I'm selling stuff, that gets very difficult to just have that complete isolation from it. But I really want to try and think as much as possible to be able to handle that if I can. I want to try and get to that point as much as just really humanly possible for this. So when I'm thinking about all of these different elements, so let's think, okay, adding that resiliency in, how can I really get that resiliency of part of my all-up solution? So I talk bulkheads. I want to limit chain reactions. Well, as much as possible, think of that resilience to some kind of problem being able to impact them all. So I might think, okay, there's some entry point, back over here. There's some entry point here. And ordinarily, I'm going to go and talk to my database. We talked about that idea of, can I add some resiliency to that all-up solution? Is there some way to handle not just cascading, not just sharing those problems through? Hey, maybe there is a queue. So if this is not available, well, can I go and write to a queue instead? Or maybe I've got the idea of some kind of cache. Maybe it's a side cache that I go and check first. If there's a result, great. If there's not, then I go to the database. Maybe it's a read through. I always go via the cache or write through even. There's different ways I can implement, but maybe I'm using some kind of cache. And as we talk about, caches can actually help in a lot of different ways. It's not just to speed things up. It can actually help in terms of my resiliency as well. So where possible, we'll have these independent items as part of the all-up solution. And when I talk about database is actually tricky. You'll always hear about with database the idea of cap theorem. You have the idea of consistency. So every read will always get the latest right. I have the idea of availability. Every request will get a valid response. Now, sometimes I'm going to split this up. Sometimes I might split up the idea of availability of reads versus availability of writes. Maybe sometimes I'm willing to give up the write, but I always want to be able to give up the read. And then P is partition tolerance. When I think of multi-regions, if there's some break in communication between them, well, do those independent instances still carry on functioning? And a database can only ever have two. Just by nature, can't have them both. And so if I'm thinking multi-region, particularly, I have to give up consistency. I have to be able to support partition tolerance. I have to be able to have a break in communication. I have to have it available. I'm willing to give up the consistency. But again, there may be things that I might split about, well, you know, I need consistency of certain levels, but maybe I can't write to it. There's different things I can handle about that. And we also, remember, talked about those bulkheads. I keep coming back to the bulkheads. This is really the most important, having those splits. But realize sometimes you have some service that's used by multiple things. So if I've got my service A, well, maybe it's used by B and C. What if C misbehaves? What if C is just hammering my service? Maybe it's accidental, maybe it's deliberate, maybe there's some bad thing coming in. Well, it then makes this sad because there's not enough resource for it to handle. So sometimes from a bulkhead perspective, those isolations, even though it's one service, what I actually might do is have different pools. So it's still service A, but I have this idea of a pool 1 and a pool 2, and they talk to their own pool. So now they can't DDoS or impact negatively the other pools. They've got no way of doing that. They don't have anything shared. I've heard examples of from sales. Hey, when I want to actually go and purchase a transaction, I go to one instance of a service. But if I'm just going looking at comments, or maybe I'm a not preferred customer, I go to a different. So I'm always protecting certain elements. I'm having those bulkheads as much as I really can. That's really the important point. The other thing I can try and do to improve is, we asked at the start, all the way back here, one of the things is, well, how do they actually communicate? Is this, for example, RPC? Is it very like a synchronous connection? Is it going via a queue? Like, how are these things talking? Because when I have these different tiers, if I can, what's ideal is to decouple. I don't want very tight coupling. So a tight coupling would be like an RPC, a synchronous call. And the problem when it's tightly coupled, if one service is moving, the other one has to move the same amount. So if there's some flood, some surge in workload, and this starts getting loads of requests coming in, this one has to equally move. So any pressure I've got, this feels exactly the same pressure. If I can decouple them, make it more loosely coupled, maybe instead of some direct communication, we'll get rid of that. What we'll actually do is this writes to some queue, some service bus, and then this takes it off. And that's like a piece of string. If this moves like really fast, this doesn't. And it's actually really good. So if this gets some surge in traffic, they've now been separated in both time and space, essentially. If this is doing a huge amount of work, this doesn't have to. If this in a period of 10 minutes got a huge number of transactions, it doesn't have to handle them in 10 minutes. It could spread that out over 2 hours. So it can buffer the work by doing that decoupling, by making it more loosely coupled. If I wanted to add functionality to here, it's not some strict call that this now has to change all its code and this has to change its code. No, it may not have to make any changes whatsoever. So it's going to make it easier for me. Integrations are typically the #1 cause of problems. The looser I can couple them, the better my life is going to be. I talked about the idea of these alternate paths. Hey, something's trying. I had the idea of caching. And it really is important to understand that cache does multiple things. So absolutely, the cache can help with performance. The whole point of a cache is it doesn't have all of the data as a database, but maybe it has the most recently used. It has the most recent select statements. So if I keep running the same select statement again, hey, I don't have to go for what is a fairly expensive request on the database. I can serve it from this, maybe it's a memory cache or it's got a bunch of SSDs, it's a higher performance. So I'm going to get those responses much, much faster. And realize this applies to both clients and servers. So some client talking to a service, but again, different tiers within the service talking to each other. I might have a cache before I talk to this tier of my service. So this can apply in multiple places. But it gives me performance boost because, hey, it's got those last set of requests I made or whatever, but it also adds resilience. Because potentially I could write into my logic, hey, if I don't get a response, let's use the last value I got. I've got a value in my cache. And we saw the example, hey, of an IP address, but this could also be, hey, maybe I'm serving up comments on something. Hey, if I can't get the latest comments, no big deal. Let's just show the last one. And Netflix is always used as an example. Hey, I'm trying to look at the catalog of movies. I'm not getting a response, but I cached the last set of movies we looked at. Let's just show that. Because the actual service to play the movie is different. So we can handle, if it's a little bit stale, hey, I can't get the latest episode of The Witcher maybe, and that's bumming me out, but I can still go and watch something. So I can have this idea of the cache. But you do want to make sure the cache is an asset. Depending on how I'm implementing this, let's say it's from the side. So I can have this idea that I can have a side cache. So the app is aware, it talks to the cache to try and get a result. And if it's not there, then it goes to the database, then maybe it writes the result. Well, that's an extra step. If it's missing all the time, it's not in the cache, this is just slowing down. It's a negative element to my architecture. So I need to make sure the cache remains an asset. And one of the ways we have to do that is the cache is a finite size. So maybe it just has least recently used, is purged away. So we have to be able to get rid of old stuff. I have a certain maybe lifetime. I have to be able to expire content from the cache so it remains useful. And there are different places I could put the cache. So you can actually think about, well, I might have a cache built into the client in memory. Or it's some completely decentralized global cache that's close to the server, say like a Redis cache. And there's pros and cons. When the cache is in the client, super high performance, it's using up some local resource, But if I have 10 different clients, each with their own individual caches, if some of them makes a change to the database, the other caches don't know. So now if I got old data, how do I keep consistency? Whereas if I have a global cache, hey, the consistency is going to be great. But now it's a separate set of services. Maybe there's a slightly higher latency because now it's going over the network. But again, there are options there to work out what's the right thing to do. And depending on my type of client, depending on the service I'm talking to, there's different approaches to what is the right cache for any solution. But the key point, the cache really has two purposes. Yes, performance, but don't forget about that idea that, hey, I can also use it as a resiliency mechanism. I can help improve my app's architecture. The other challenge is like, well, okay, go and write to a queue. When? When do I know as the application to give up? What's going to trigger me to say it's not working? So if I'm the client, I'm trying to do something. I'm trying to write to that database. Now, what you see in code a lot of the times is if it fails, we'll just retry straight away. Very few things in computers, and think how fast computers run, instantly fix themselves. And we've all heard these stories about some service had a problem and it DDoSed itself to death because it has a problem and it's not responding. And so all the clients just hammer it. Hey, help, 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 answer, answer, answer. And everyone just starts piling on and it just gets worse. So we're making the situation much, much worse by just continually hammering the service. And there's almost no chance it's really going to do anything useful. So a much better option is, well, don't just instantly retry. Put in some kind of wait. So wait for some period of time. And then sure, we can try again. But there's also, at a certain point, we need to go the alternate route. At a certain time, I need to switch. I'm like, okay, this isn't working. I need to switch over. And we'll often hear something called the circuit breaker. We have them in the houses. If there's too many things on a certain circuit that's drawing too much load, the wire would heat up and it would burn our house down. And so circuit breakers, they'll flip off. They'll protect ourselves. So, hey, we see the failure, rather than just letting it go and degrade, we're going to flip off. But then after a period of time, we can go and flip it back again. Something's got resolved, then we'll bring it back to life. Same idea here. We try, we wait, there's another error, okay? At a certain point, we're just going to stop and the circuit breaker would kick in and we'll take the alternate path as one is available to us. Now, how do we know when to trigger? There's different patterns for this. A very simple one, you'll hear something called the leaky bucket, which itself sounds like a problem. But the whole point of the leaky bucket is there's a leak in it. Every time there's an error, so hey, the try failed, well, you pour some errors into the bucket. So it builds up. But also at a certain period, maybe every 10 seconds, it lets an error fall out. So if, yeah, I'm getting sporadic errors, but we expect a certain amount of errors, a certain amount of errors fall out. So hey, random errors are coming in sporadically, but also we let a certain amount fall out at a certain period of time. Now, if we get a sudden surge of errors, they're not leaking out that quickly, so it would build up, and then if it reaches a certain critical point, then we'll trigger the circuit breaker, then we'll go the alternate path. Meanwhile, they'll continue to leak out, the errors would stop because we're not going to the bucket anymore, and at a certain point we say, hey, let's retry again. Maybe it's fixed itself, and if it does, then we'll switch back to the database. So there are patterns we can put in the application to help. And the circuit breaker and combine that with the leaky bucket can really help taking the pressure off of a service that's struggling, but also keeping the rest of it functional. And that's an important part. We'll often talk about fail fast. Fail fast was the same we'd say with small businesses. It's better to fail fast. Hey, if the business is not going to work, just fail. Don't linger for years hemorrhaging money. If it's not going to work, just fail fast. It's the much better thing to do when I'm starting a business. Ideally, you don't fail fast. Hopefully you succeed. But if you're going to fail, let's not drag it out. Same applies here. If I'm making some call to something, if I'm some service, it's better to just fail the request if I'm not going to be able to handle it, rather than having some long timeout and drag it out. Because what am I doing? I'm consuming resources on my side. I'm making them wait, which is tying up resources, which may propagate out to things calling them. It's better to just fail it, let them have some error handling and move on. Let's validate calls to make sure I'm not going to experience some call later on because I passed in crummy values. So all of these things really build together. And there are many best practices when I think of all of this together. So hey, we have the idea of the infrastructure, we have the idea of the application. One of the things we really want to try, I guess I'll draw it over here, across all of this is I do want to try and maintain as much as possible this idea of a steady state. It's very common that we put in some new service, it's happy, it's fantastic, and then certain things build up over time. My disk starts filling up, a database starts filling up, a log file starts filling up, a cache starts filling up. Any data that I'm adding to something, so anything that's being added, I want some similar process to be purging. So I stay in a steady state. I'm not hemorrhaging disk space or cache space or memory or logs or whatever, unless this is deliberate. If it's deliberate, then I should be planning for that. But make sure I've got some kind of, as stuff's being added, there's something purging. So I'm not filling up and just eventually going to fall over. Avoid humans. Don't let humans touch things. Humans generally, we're going to break things. I want really good testing. So we have this idea of kind of test, test, test. There's Azure load testing, which can help run your JMeter scripts to do these bulk testings. Have a test harness that can test different scenarios of the application. And very often people will skimp on the testing. They're in a rush. But realize the more I skimp, again, it's what's that important thing to you? I skimp on the dev, I skimp on the testing, it's going to bite you in the production. People will always find the bug that you didn't think of. And that's actually a great point. Hey, I can test all I want, but I'm never as imaginative as reality. It's always going to beat me. So you get into this idea of like chaos engineering. Azure has this Azure Chaos Studio. I can actually go and simulate different types of failures. A rack fails, a data center fails, an AZ fails, this happens. Reality is more creative than me. Let's try and simulate those things. In an ideal world, I'd try and do some of this in production, but depending on the criticality of the system, that may not be practical. If I run it in non-prod, I really do want to make sure it's as close to production. Maybe it's scrubbed production data, so it's actually real types of data, but I've moved any PII, anything that would be sensitive to that. Make sure my ratios. If this is a 20:1, I want a similar ratio because maybe it breaks when there's some contention, there's some locking. If I'm a 1:1, there's no locking. There's no one contending with the process. But if it's 20:1, well, there's a much greater chance that that's actually going to happen. So I want to be able to safely inject failures, but I do want to be able to see those. I need to make sure I've got great monitoring. I want that observability, that's supposed to be an I, looking at everything I have going on. And we're looking for signals of failure. And those signals could be some spike in traffic. Signals can also be an absence of signal, which sounds bizarre. But maybe I'm expecting something to be generating or making some, and it's not. It's completely silent. Well, that's maybe a signal of a problem as well. I want to have a really good idea of what is healthy. I have some baseline of healthy, so then I can detect when it strays from that. So all of these things are really important when I think about my all up meeting my SLA. My whole point of this whole presentation was often when we think of SLAs, we go and focus on the infrastructure. And absolutely, I need the infrastructure there. It's half of the story. And as we saw, there's ways I can improve the SLA of the infrastructure by having alternate paths. Make sure you consider, well, what splits, what makes a decision between the paths? Well, can I add some resiliency there by maybe some caching or some alternate path? But it's really the application. I need to make sure it has those same concepts. It has bulkheads. It has independence. It doesn't have some shared dependency. It has the ability to scale. It has the ability to think and take those alternate paths. I don't have some death spiral where one thing fails and it's going to have this cascading failure to bring down everything else. I have bulkheads, and those bulkheads are critical wherever I can to lessen the impact of anything actually happening. If I can build an intelligence, hey, the circuit breaker, something's failing, at a certain point, I'm flipping it off, I'll take an alternate path. And then at a certain point, I'll retry it again. So I have these different options. So understand my requirements. Understand what can fail. Understand the considerations around the infrastructure, the app, the operational elements. How can I loosen dependencies? How can I decouple those to give me better actual resilience? Better, hey, if this thing is going nuts over here, it doesn't have an equal effect on this thing here. How can I loosen that up to give this more time to handle it? Good application architecture, good observability, good idea of my health models. If I pull those things together, hopefully I can architect to actually meet my application's overall SLA and availability requirements. So as always, I hope that helped. Until next video, take care.